So this is session number 2 in module 4. In the first session, we discussed about some of the informal design guidelines for relation schema and then introduction to normalization. So right now, I'm going to explain the concept which is required for implementation of normalization process. So that is functional dependencies, inference rules, and algorithm for determining closure of functional dependencies, and then two set of equivalence functional dependencies. So if you have a set of attributes that is called as x and y from the universal relation schema R, then we can say that x determines y. We have a universal relation schema R, and if we have a subset of attributes x and y in R, we can write it as x functionally determines y, where x is called as LHS and y is called as RHS. X is called as determinant and y is called as dependent. So X functionally determines Y. These functional dependencies are constraints. So, and these dependencies are derived from the meaning of the relation and interrelationship of the data attributes. So, we require functional dependency concept and key concepts to define the normalization process. And these functional dependencies are used to measure the goodness of relational designs. So we say that a set of attributes X, it may be one attribute or more than one attribute, functionally determines a set of attributes Y if the value of X determines the unique value of Y. That means if I know SSN of employee, that is employee ID, I can determine his employee name, date of birth, age, salary, and rest of the details. If I know USN, I can determine the details of the students. So diagrammatically, functional dependency is denoted like this. SSN determines e-name, and then SSN and project number together determines hours. Project number alone determines project name and project location. This is the diagrammatic representation of functional dependency. So this functional dependency holds if two tuples have the same value for x, then they must also have same value for y. The condition says that on a relation state R of R, if we have T1 of x is equal to T2 of x, then we must also have T1 of y is equal to T2 of y. So this functional dependency is a constraint on relation state R of R. So, and these functional dependencies are derived from the real world constant. Schema designers specify these functional dependencies. Semantically, more obvious functional dependencies can be specified by schema designer, but we may have other extra functional dependencies. It is a property of relation schema. It's not a property of relation state, and relation extension or relation state or a table should have to satisfy functional dependency. So on this constraint, it is a constraint, and the functional dependency constraints are called as legal extensions of R. Now for this definition, let us take this example. For any two tuples T1 and T2 in R, let's call this as R. This is T1 and this is T2, and this is X attribute, supplier is X attribute, and this is Y attribute. If we have T1 of X is equal to T2 of X, then we must also have T1 of Y is equal to T2 of Y. So S1 is there, T1 of X is X1, T2 of X is S1, and T2 of Y is equal to Bangalore. S3 Bangalore is there. So now I can say that supplier determines city. Supplier determines city. If this is the case, let's say S5 Mysore, and then S5 Tumkur, then so the functional dependency does not work good because it is violating the conditions. The T1 of X is equal to T2 of X. That is right. First condition is met. Second condition, T1 of Y is equal to T2 of Y, which is wrong. T1 of Y is not equal to T2 of Y, which is wrong. We have one more definitions of functional dependency. Yes, this one. If a key, that is, if a constraint on R says that if there cannot be more than one tuple with the given X value, consider this diagram. We have one more tuple with the given X value S1, S1. The constraint on R says that for a key or tuple needs to be distinct, unique. S1 and S1 is repeating here for candidate key or for a primary key. So that should not be the case. If a consent or R says that there cannot be more than one tuple with a given X value, then X is a candidate key of R. So X is going to determine the rest of the attributes. So in the diagram, SSN is the candidate key. It can determine employee name, birth date, address, D number, D name, DMG, SSN. If we have a primary key, then primary key is going to determine all other rest of the attributes. In the second example, employee project, we have SSN and project number as the primary key. So primary key is going to determine rest of the attributes. So we have one more example here, and we have three constraints. Which constraint holds good and which constraint is not going to be correct, we'll discuss here. Text determines course. That means if I know the author name, this is author name. Andrew S. Tannenbaum, he has written data structures. Ronald B. Adler, he has written data structures. So R.S. Pelagatti, data mining. Jeffrey D. Ullman, language processors. So text determines course. So this is fine. If I write it as course determines text, we have to check whether it is right or wrong. Course data structure. If I know data structure course name, is it possible to tell the teacher name? No, because for data structure we have two teachers. I cannot say it as course determines text. Sorry, this one. For course data structure, we have two textbooks, that is Ronald B. Adler and Andrew S. Tannenbaum. So this functional dependency does not going to hold. Teacher determines course. Harry means if this is different name, John, then this functional dependency could have holds good here. So now Harry is repeating twice, but T1 of X is equal to T2 of X, but T1 of Y is not equal to T2 of Y. This functional dependency also not hold good here. So that is the definition of functional dependency. As I said, this will be specified by schema designer who know the actual meaning of the data. So these functional dependencies will be specified by schema designers. So examples of functional dependency constraint: SSN determines CNAME, project number determines project name and project location, and SSN and project number together determines hours. Because without project number, we can't predict how many hours an employee can work on. Employee should have to work on some hour, work on particular project for some hours. And only using project number, it is not possible to determine hours. So both these keys are very much required, SSN and project number. In fact, this should be the key in this employee project relation. SSN and project number together determines hours. So the slide says that it's a property of the attributes in the schema R. And this functional dependency constraint should have to hold on every relation state R of R. So we have 6 inference rules. As I told, the schema designer is going to specify only the semantically obvious functional dependencies. We may have other functional dependencies that holds on relation state. So that satisfy the dependencies in F. So to infer or to obtain these other functional dependencies, we can use these inference rules. We have 6 inference rules: IR1, IR2, IR3, IR4, IR5, and IR6. But here IR1 to IR3 are called as Armstrong's inference rules. As I told, these IR1, IR2, IR3 are called as sound and complete set of inference rules. We'll try to see like what is the meaning of sound and complete set of inference rules. Maybe after the explanation of this particular slide. So we have a reflexive rule. It says that if we have y as a subset of x, then x determines holds good. If it is something like this, if x is a superset of y, then x determines y holds good. Also, x determines x holds good. According to the reflexive rule, x determines x holds good. So for example, if SSN and department name, employee name determines employee name, because y is a subset of x, this functional dependency holds good. SSN comma employee name determines employee name. So this functional dependency satisfies reflexive rule. I can write it as SSN determines employee name. SSN and employee name, because y is subset of x. And also SSN determines SSN holds good here. SSN determines SSN holds good here. Augmentation rule. If you have a functional dependency X determines Y, then we can write it as XZ determines YZ. So we are augmenting one attribute here. So if I have something like this, SSN determines employee name, then along with this I can write it as SSN comma department number. I'm adding one attribute, together determines the employee name and department number. Okay, XZ determines YZ, where Z attribute is department number. Transitive dependency. If you have functional dependency in the of the type X determines Y, Y determines Z, then X determines Z holds good. So in the diagram, you can see here, SSN determines department number. Through department number, I can determine DMGR SSN. So I can write it as SSN determines DMGR SSN. DMGR SSN. So this is called as transitive dependency. Okay, example we have discussed, SSN determines department number, and then using department number, if I know the department number, I can determine DMGR SSN. So indirectly, I can say that SSN can determine DMGR SSN. DMGR SSN, that is manager of the department. Manager of the department. So we have three more inference rules right now. That is decomposition rule, union rule, and pseudo transitive rule. So we'll discuss this decomposition rule. If we have a functional dependency X determines YZ, then we can write it as X determines Y and X determines Z. Let's take one example. SSN determines employee name and the department number, that is true. I can write it as SSN determines employee name and then SSN determines department number. SSN determines department number. So here we are actually decomposing two attributes into single attributes towards right hand side. Union or additive rule. In the case of union or additive rule, if you have X determines Y, X determines Z, then I can edit as X determines YZ. So I'll take the reverse of this one. If I have SSN determines employee name and then SSN determines department number, I can write it as using union or additive rule. SSN can determine employee name comma department number. This is union and additive rule. Pseudo transitive rule. So X determines Y exists, then WY determines Z, then I can write it as WX determines Z. Pseudo transitive, where here Y is pseudo transitive. So let's take one example. SSN determines SSN. Let's call SSN as X and this side RHS as Y, and then project number comma SSN determines hours. So this hours as Z, this as Y attribute and this as W attribute. Then I need to write it as W, take project number, what is X, that is SSN, what is Z, that is hours. Now here Y is pseudo transitive. Attribute Y is pseudo transitive. So these are the 6 inference rules. As I told, the last 3 inference rules as well as other inference rules can be used to deduce other functional dependencies. IR1 to IR3 are called as sound and complete inference rules, are also called as Armstrong's inference rules. Sound in the sense, if we have a given set of functional dependencies, so any dependency that we can infer from F by using IR1 through IR3 holds in every relation state. So that satisfies dependencies in F. That means all the functional dependencies holds on every relation state. And complete means We cannot infer any other functional dependencies. So that will be the last set of functional dependencies. Additionally, it is not possible to infer any other functional dependencies. It gives the complete set of all possible dependencies. Using any of the inference rules, all the 6 inference rules, it is not possible to obtain additional functional dependencies. So that is called as completeness property. So now we'll discuss closure, the definition of closure. Closure of set of functional dependencies is denoted by F plus of all functional dependencies that can be inferred from F. That means if we have a set of functional dependencies F, we can infer or obtain additional set of functional dependencies that is called as closure of F. Closure of F is denoted by F plus. So a systematic way and a correct way to determine the closure of F is to determine the left hand side of the attributes, that is called as X attributes with respect to F, and then determine X plus the right hand side of the attributes that are functionally determined by X. This X plus is called as closure of X under F, can be calculated by repeatedly applying IR1, IR2 and IR3 using functional dependencies in F. Now I have one example here. So this is the given set of functional dependencies. I need to calculate F plus. F plus contains additional set of functional dependencies other than these 3 functional dependencies. So we have 3. We can infer 3 more extra functional dependencies. So that we have to keep it in F plus. That is called as closure of F. We have an algorithm, as I told, the first step is to determine X, that is left hand side of the attributes, and then determine the attributes that are dependent on X. Let F be the set of functional dependencies in relation. So consider this is set of functional dependencies F. For each functional dependency, Y determines Z in F. That means for all the functional dependencies, 1, 2, 3, 3 functional dependencies are there. So if for each functional dependency of the type Y determines Z, so this is Y determines Z. Y determines Z. If Y is a subset of X plus, that is X plus is, if Y is a subset of X plus, then X plus is equal to X plus union Z. Repeat until no more attributes are, repeat until no more attributes are available. Okay. So we have to determine. So repeat until no more attributes are added to X plus. We have to determine X plus. We'll use one example here. So now let's take this is F. Set X plus is equal to X. That is SSN plus. I'm using this one. SSN plus is equal to SSN. Now second step. For each functional dependency, Y determines Z. This is functional dependency. Y determines Z. We'll take up the first functional dependency. If Y, that is SSN, is a subset of SSN, then X plus is equal to X plus union Z. That is X plus is becomes right now SSN comma employee name. That's it. That one we have written here. SSN plus is equal to employee name and SSN. Consider the second functional dependency, that is project number determines project location. Y determines Z. Check Y is a subset of X plus. No, project number is not a subset of SSN and employee name. SSN and project number is not a subset of SSN and employee name. We have to consider these two together. So we have done with the first step. For first attribute, we have done. Next attribute is project number. Project number plus. Consider the first attributes. SSN determines C name. Y determines Z. Y is not a subset of X plus. X plus is this one. Okay, leave out the first functional dependency. Second one, project number determines project name and project location. So X is, Y determines Z. Y is a subset of X plus. So add. So X plus becomes project number, project name, project location. This is my X plus, new X plus. Right? Project number plus is equal to project number, project name, project location. Consider the third one. SSN, comma project number determines hours. So SSN and project number is not a part of this one. So we will leave out this one. Now consider the third attribute, SSN and project number. SSN and project number plus. This is X plus. X is set to X plus. This is X. X has taken to X plus. Consider the first one. SSN is a part of SSN and project number. Add E name. Union Z. X plus is equal to X plus union Z. E name you added to X plus. Next, consider project number determines project name, project location. Project number is a subset of this one. Add P name and P location. P name and P location. SSN and project numbers determines hours. So this is left hand side is a subset of X plus. Add hours. So my third set of functional dependencies SSN and project number plus is equal to SSN project number E name P location and hours. So that's it. That is with respect to closure of the algorithm. So along with these three functional dependencies, F plus is going to contain 6 functional dependencies. X plus is total this one. These three plus whatever the additional functional dependencies that we have inferred. SSN determines C name and SSN. Project number can also determine project number, project name and project location. And SSN and project number together determines SSN, project number, E name, project location and hours. Earlier with this set of functional dependencies were not available in the original list. So we have inferred using what? IR1 to IR3. We can say two set of functional dependency. Next topic is equivalence of set of functional dependencies. If we have a two set of functional dependency F and G, and we can say that equivalent if F plus is equal to G plus. We know how to calculate F plus and G plus. If F plus and G plus are equal, then we can say that both set of functional dependencies F and G are equivalent. F covers G if every functional dependency in G can be inferred from F. That is G plus is a subset of F plus. F1 G are equivalent if F covers G and G covers F. That means every dependency in G can be inferred from F and every dependency in F can be inferred from G. So we have an algorithm for checking equivalence of set of functional dependencies. So that's it. Thank you.